Thank you, Innocent. Davies speaking. So we will work together with Safaa to identify early prognostic markers of Alzheimer's disease for primary prevention indication. As you've been told, it's an extension of work done by two pairs of previous APT fellows. These were projects done last year. So just a bit of background to what we are dealing with. Alzheimer's is a complex neurodegenerative disorder with usually pathology beginning about 10 to 20 years earlier before symptoms appear. And an estimated 300 million worldwide are affected by this disease. This is generally characterized by impairment in cognition, daily function, and neuropsychiatric symptoms increase as the disease progresses. Histopathologically is characterized by the two hallmarks that you see there, beta amyloid and tau accumulation. The graph that appears below there, as time progresses, the biomarkers, the amyloid, the tau, and the degeneration increase. And you see these graphs, they appear much earlier. And when cognitive impairment appears on the last graph, the background, tau, amyloid, and neurodegeneration has already occurred. And multiple risk factors usually contribute to this, maybe some more equally than others. And as you can see, there are some modifiable, others non-modifiable. And to this effect, keeping in mind the multiple risk factors of the disease, we can look at the disease continuum on this next image. A lot of activity occurs right in the middle for secondary prevention and early symptomatic, and multiple companies work in this space. Lilly, our sponsors included, to try and mitigate this problem. But you notice at the tail end of the activities, there is not much activity that happens. On the tail end to the right where my cursor is, on the moderate to severe end, not much happens there, and cognitive and functional impairment has already taken place. So we focus on our efforts on the asymptomatic phase, as you see there. And this is important as it may slow down or even retard progression to severe disease. So to bring you up to speed, so the previous fellows in two independent projects, Marwa and Noel, worked to quantify natural amyloid plaque accumulation. And this they did along the disease continuum, all the clinical stages of Alzheimer's disease. And they developed a natural amyloid plaque disease progression model and tested covariates and found that age, gender, APOE4 disease genotype was significant, affected disease at baseline. And then, as you had been told earlier, Innocent and Bongi worked on machine learning assisted covariate screening of correlated covariates, and they applied these techniques to PK data of the C-pyramid. So our work, the Safaa and I worked to merge these two concepts to now try and identify the high-risk population to target for AD prevention, and using machine learning techniques as a pre-screening tool for these large number of covariates. So the two objectives there, one for myself and Safaa. So Safaa, using the previously developed disease progression model, used machine learning techniques to evaluate the wider set of covariates which he will tell us about. And myself developed a new disease progression model looking at tau accumulation, keeping in mind the two hallmarks of the disease. And once that was done in the A4 dataset, we now evaluated the machine learning techniques to explain baseline disease state for the participants in the A4 dataset. So at this juncture, I'll hand over to my colleague and who will take us through a bit of the methodology.
Hello, everyone. So this is Safaa Ibrahim. So thanks, Davies, for introducing our project. So from now on, I will introduce you to the workflow that we worked together, like to do actually to apply both like the developing the disease progression model and using the already developed one and applying the machine learning for screening of covariates. So here, as you can see here in the top of the slide, this is summarizing the model definitions, the simulation settings, the data generation, and model estimation. From the left side here, we can see these are the inputs as data set. Like we are having two main objectives. So we have two different data sets. One data set, the ADNI data set, where we apply the amyloid accumulation disease progression model. On the A4 data set, where Davies developed his tau natural accumulation disease progression model. We have different sets of covariates in each data set that we will talk about it later. We consider the covariate distribution, the correlations between continuous covariates while we are doing simulation. For the natural disease progression model, we developed it in monoliths. So the previous one, using ADNI data set for the amyloid accumulation, was developed on non-men, and we were able to replicate the disease progression model using monoliths. For A4 data set and for developing the accumulation of tau, Davies explored different models that he will talk about it later. So we used R and monoliths. So for R, we code the structure model using monoliths by R, which is packaged for the soft connector. Our covariate data set was not complete, so we imputed using different methodology. We simulated 100 data sets, replicating the number of the subjects that were already in the original data set. We added covariate effects while doing the simulation, and we added the 4 covariates, as Davies mentioned, that the previous cohort defined 4 significant covariates, which were 3 categorical and 1 continuous. And considering the same covariates, we consider for A4 data set, but since the A4 data set is a preclinical data set, so we didn't include the diagnosis at baseline. So there are 3 covariates. For monoliths, we made the structural model for each of the simulated data set, generating the EDAs and betas for each simulated data set. And then we move forward with the covariate selection using either the pharmacometrics techniques or machine learning techniques. So we run the pharmacometrics technique using the monoliths by R. We tried running the SCM, the POSAC Samba. For machine learning, we use the carrot package. We run the different methods like linear regression, stepwise linear methods, penalized regression, random forest neural networks. And after that, we compute the variable importance and rank the methods, including the pharmacometrics techniques, using the F1 score, which is considering the accuracy of the technique. So we did that in whether we consider the correlations between covariates or not. So starting with the objective number 1, where we are using the amyloid plaque accumulation disease progression model and ADNI dataset. So ADNI dataset had a wide variety of covariates. So it has MRI, PET images, genetics, cognitive tests, lots of biomarker from blood or from CSF as a predictor of the disease. And as you can see on the right side, this is the ADNI patients included in this study. There are a total of 1,291 participants that are considered in this study. Most of them, they were white and non-Hispanic, non-Latino. About more than 50% of the participants were A2E non-carrier. As you can see here on the left side, this is the profile of the amyloid in different Alzheimer's disease stage, ranging from cognitively normal participants to the Alzheimer's disease. So this is our final disease progression model. So it's exponential model for accumulation of amyloid. These are the estimates on the left side that we were able to replicate what I have done last year with using monoliths. And this is the interpretation of the covariate effects on the disease progression model parameter. For example, if we have A to E heterozygous or homozygous, so we will see like an increase of the amyloid at the baseline by 13% or 19% respectively. These are the VPCs stratified by the disease stages. So moving forward to the covariates, so any covariates that we consider for screening, there are total of 37 covariates. We have in different classes like CSF-based biomarkers, imaging-based biomarkers, structural MRI variables, cognitive scores, functional scores, and also considering like clinical and demographics. So in total, we have 31 continuous covariates, 6 categorical covariates. So we have about 50% of the subject has missing data. So in the next slide, I'm showing the diagram and the workflow also how we dealt with that. So first we did the imputation. So we have, in the beginning, we have incomplete data set. So for the above limit of quantification and below limit of quantification values, we use the M3 method. And for other missing values, we use the multiple imputation like chain equation in the data set. So we did imputation, we generated 100 imputed data set, and then we merged this data set. After that, we moved to simulation. For doing the simulation, we consider the distribution of the categorical covariates and the correlations between the continuous covariates using the Fox package in R to do the simulation of covariates, and we use also the base model and the true covariates effects of the 4 true covariates for simulating the DV. And now we are having 100 simulated data set. Moving forward, we then generated the etas and thetas for the 100 simulated data set. And for the etas and thetas, we apply the machine learning method. And for the simulated data set, we use the pharmacometrics method for covariate selection. So these are in this figure, we are showing here the results from running the covariate selection methods, pharmacometrics methods, as well as the machine learning methods. So on the left side, you can see here, this is the percent selection of covariates. In this figure, we are not accounting for the correlated covariates. So as you can see here on the x-axis, you can see here the method, and between parentheses, this is the F1 score, which represents the accuracy of the method to detect the true covariates. So we have 4 covariates, and we can see here the AIC stepwise machine learning method performs the best and giving it the highest high score, even without accounting for the correlated covariates. However, when we account for the correlated covariates, you can see the performance of the other methods performed better, especially in detecting the gender and diagnosis. So I want to drive your attention here that the machine learning methods are faster than the pharmacometrics methods, as you can see here from this table. So the above till the IC stepwise, these all are the different machine learning methods, and as you can see, it takes like seconds or minutes to run for per simulated data set. However, using other pharmacometrics methods, Cosac and Cosac Samba, it takes like about more than half an hour, but for SCM, it takes like for only one run, it takes about like 7 hours. So in conclusion, for the first objective and next steps, so AIC-based stepwise selection machine learning method performed the best, that it gives us the highest F1 score. Also giving into consideration like the machine learning methods runs faster than pharmacometrics methods by 26-fold for Cosac methods and for 284-fold for SCM. So for next steps, we want to apply the AIC-based stepwise selection as well as also Cosac method. on the original data set and see the selection like of the covariates. By that, we hand over to Davies to discuss his section.
So thank you, sir, for taking us through the amyloid component of this particular project. So I worked on developing a disease progression using natural tau accumulation from the A4 dataset, and use the same steps with very minor variation to use now to evaluate the wider set of covariates using the machine learning. So for the A4 dataset, we use the placebo arm of this particular trial. In the A4 trial was an early interventional trial that aimed to slow cognitive decline in a preclinical stage in patients who had elevated amyloid levels on PET scan but had no cognitive impairment at baseline. So just a disclaimer here, the early is in reference to the disease stage, not necessarily the age of the participant. And so the placebo arm had about 181 participants, and they had data on the novel biomarker, the plasma p-tau, that is one relatively non-invasive in quotes. It's compared to the CSF-based biomarkers and the MRI-based biomarkers that usually take quite some time. And the plasma p-tau has been shown to differentiate between Alzheimer's and other neurodegenerative disorders, and two is also fairly sensitive for Alzheimer's disease progression. So this just shows the demographic participants, more females than males. We noticed that since this was a trial, patients were mostly recruited from the US, as you can see. So the race was white, and majority of them were recruited from the United States. And I'll just take your attention to the APOE4 carrier status and the genotype. So the purposes of this study, this is how we categorize them. So patients with the E2, E3 allele and they were non-carriers, we consider them low risk. And any patient with the E4 allele was considered high risk in quotes. But if you had E2, E3, we considered you intermediate risk. And if you had both the E4, which has been shown to be to drive accumulation of amyloid and tau in Alzheimer's disease, then you are considered high risk. So our disease progression model, we found that the exponential model explained our data quite better. Although you notice the objective function value between the linear model and the exponential model, not much of a difference, but because of biological basis of disease, then we chose the exponential model. And the figure on the right of that then shows the covariate effects for this particular model. We took the true covariates from the previous work as age, APOE, and gender, but now estimated those effects for this particular data set. So the next slide is to show you some of the goodness of fit plots, and what's it called? The VPCs were acceptable, and you can even see from the observation and the individual prediction, the spline line did not deviate too much from the uniformity line. So the covariates in our particular data set, majority of our biomarkers or covariates were clinical and biochemical, and the absolute values, you can see them from the top left. 5 were about for cognitive function scores. 1 was the PET scan that you remember we had mentioned was part of the screening criteria, and the blood-based AD biomarker. So plasma beta amyloid 1 to 40 and the other 1 to 42. So in terms of what we found for this particular data set, the linear regression ranked highest in both scenarios. And by scenarios, I mean when we accounted for correlated covariates and when we didn't account for correlated covariates. So in this particular slide, the without accounting for correlated covariates, linear regression had the highest score, although not too high. Managed to pick out the true covariates for the risk traits 12% of the time, gender at 6% of the time, and age 87% of the time. And you notice the same for the pharmacometrics methods here, COSAC-SAMBA and SCM. SCM didn't pick up the APOE, and COSAC-SAMBA picked it up once when not accounting for correlated covariates. But when you account for correlated covariates, we notice that our methods managed to pick up the correlated covariates, the true covariates. But linear regression also ranked the highest in both scenarios. Yes, linear regression ranked highest in both scenarios, but I'll take your eye to the pharmacometric methods did not do so well compared to the machine learning methods. And so for this particular data set, remember, Safaa had about 1,000 participants, myself had 180 participants. The machine learning methods, runtime per data set was in seconds, and you notice for COSAC-SAMBA about a minute or two per simulated data set, and the SCM took about 10 minutes for this particular data set. So in conclusion, for this particular, for the tau accumulation, linear regression ranked the highest for covariate selection, but this was when accounting for both scenarios, but we noticed that it did much better when accounting for correlated covariates. So our next steps going forward is to extract the frequency of the selection for the other covariates tested, and now also test these machine learning methods and the pharmacometric methods to the original data set. And with that, I want to thank Sitara, Pharmacometrics Africa, and the Lilly for walking us through this project and to this particular point. Thank you.
Thanks, Davies and Safaa. I've been monitoring the chat. I don't see any questions. I don't know if anyone in the room wants to ask. Probably, Colin, I'll hand this over to you because you can see better those in the room.
At the moment, I don't see any comments, any hands up yet. Go ahead.
So I want to ask about the data set. The all subjects start at the same age.
No.
Start at a different
Yeah.
age.
Like for example, ADNI dataset is actually like a database. So it started like since 2004, at least as far as I remember the number. And actually for ADNI, it started with ADNI 1, which is like recruiting older people. And actually, for example, in our data set, we have it like from 55, the range is like from 55 to 91. So, but actually these are like, we have like 4 cohorts, and actually we are considering that as a covariate in our, one of the 37 covariates that we have. So they are not recruited at the same time. So the aim of the ADNI is, it's like recruiting the older people, and then they do the PET scan, and they do, and even like do the biomarkers, biomarkers, genetics. So to have a database, and this would be available for researchers like to help in defining the stages, defining the clinical trials. So it helped like to understand the disease and defining the population, so we can define like clinical trials and then to intervene with the experiments.
This I'm asking, I feel like any of your thoughts, it goes by time versus by you wouldn't expect that any of them to be on the same, most of each other at zero. Because they are at different stages in their life.
Yeah, and even in recruitment, so you can have someone recruited at and having in different stages. Like you can have 160,
okay,
but
show us
maybe
one of your thoughts that are time versus time course spaghetti plots.
Innocent, can you follow the conversation as well?
Yes, I can.
Yeah, like this. With the APC plots that
Is ADNI or is it? Because we have two different
yeah,
data.
either way, The point I'm trying to make is nothing connects these people as far as the time goes. Time zero, there's nothing that connects them. Because somebody could be 75, the other could be 82. Their biology should be different.
Yeah.
Should these plots be aged?
We had this conversation with the sponsors, and
Yeah.
actually we had this conversation like maybe for different meetings, whether how can we consider the time? Because actually the disease progression model that was developed before, it used this data as is, like as considering without modification. So our sponsors were really concerned about like modifying the data set. So
I don't think you need to modify it. I just think to visualize it, to plot,
Yeah.
to show at APC.
So I don't know if I get your question. Time zero is time when you are recruited. So that was, so even if you are recruited 5 or 10 years earlier, okay, it would be, that was regarded when we were testing multiple models, but time zero is regarded when you are enrolled into the observational study, which was early. For the A4, it was quite straightforward because it was a clinical trial, but for the ADNI, time zero is considered time at first contact when you got into the study. So yes, we are cognizant of the fact that many people, you come in very, very differently. One is much older with higher tau level, higher amyloid levels. But I think for me, that's the advantage because it now increases the diversity of what we see rather than a clinical trial.
Just think to visualize it.
Yeah.
Look for trends. You want to talk to at least subjects at the same scale. So you can say, okay, they increase this way, they move up in a linear way or a power.
You can review the literature. More and more we see disease progression models with age. The models continuum across age. And it's a common issue in any database, non-interventional type of trial. You don't really have a baseline. It's okay, you start following people at random time. So you need a way to normalize those. So that can be a good idea for the future.
Yeah.
So another model, which
Sorry, Innocent, I had a question.
okay.
So I didn't see you looking at effect size. It's good that you detected the covariate. But what if, like, especially in disease modeling, pharmacometrics, I'm interested to know, okay, can I detect covariate? Fine. But how biased I am? Okay, you detected upwards covariate, but you are twofold the lower or higher. So I was wondering whether you are looking at not only whether you detected a covariate, yes, no, but how about the effect size that you estimated?
So sorry. Yeah, so for this model, we decided so this work built upon previous work. So we decided to use the estimates, which the Mara and Mara and colleagues previously reported. So of course that's where we assume those were the true covariates. But yeah, you are right, because the aim of this, we want to find additional covariates. So probably we need to test with smaller effect sizes and see in case the additional covariates have smaller effects, will we be able to detect them? So yeah, I think we will need to add that in the what going forward.
And by definition, like when you have confounding corrected covariate, you might say, oh, this effect is due to another covariate that's not really true. That's the source of the effect. But yeah, maybe for the future. Thanks.
Yeah, so there's a lot of work which we are planning after PAGE. And so the previous speaker mentioned about the time. So one of the models we actually want to test is the hockey stick model. So hockey stick, it will sort of estimate when you start progressing. So that when you start progressing, because currently time zero is arbitrary when you join the trial, which we are aware of. So when we use like the hockey stick model, which will estimate when do you actually start, when do you get the when do you get the when do the symptoms kick in, when do you start progressing, when do the amyloids start moving up? If you can estimate that time point, then you can follow what you have a baseline where you start following up patients from. So we plan to also test that and then compare, see how it will compare with the current results.
Innocent, I also want to acknowledge Noel is in the room, and he was part of the team that had worked on this on these data sets the last time. Noel as a poster at Page on his work from last year. Noel, just wave your hand there so they know that it's you.
Yeah, big reform conversation, interesting conversation. Yes, sure.
And Mara is online. Mara, you could also wave if you are.
Maybe not a question, but a comment. Make some statements around machine learning methods and pharmacometrics methods, and I hope very soon as we start to adopt more and more machine learning methods and pharmacometrics, that we will consider them as two different buckets. Maybe just go with machine learning methods and traditional methods. Because I don't want this to be a distinction. Machine learning method is not a pharmacometrics. This machine learning is just an approach in which we can pharmacometrician that you can leverage. You don't need to think they are not using a pharmacometric. Just for that.
I actually like the comment. It occurred to me every time I saw it, but I don't know why, and you've nailed it.
Can you repeat it for us when we didn't hear it well?
No, I saw the presentation, a couple of statements that say machine learning methods behave, faster or better or so than pharmacometrics methods. And I wanted to make the comment that hopefully as pharmacometricians start to adopt more and more machine learning methods, that machine learning methods are not considered non-pharmacometric methods. All of these are approaches or methods that pharmacometricians can use. And maybe in the future we can use a term like machine learning methods are better or whatever than traditional methods, something like that.
Yeah. I like Ahmed's comment. As pharmacometricians, we always adopt the latest quantitative methods. So it is one of the methods that we will be using. So it is part of pharmacometrics. So, yeah.
Okay, so Ahmed, we'll modify the slide there. And we will.
So in the future came
So one of the reviewers asked us, so you see linear regression. So the question was, is linear regression a machine learning method? And our response was, so it depends on the context. So machine learning as itself, probably it's not the technique. So if I used a COSAC within the machine learning framework, I would call it a machine learning technique. So yeah, it's right. We shouldn't be differentiating them with machine learning versus PM pharmacometrics methods. But sometimes for the audience, which is used to seeing pharmacometric methods, sometimes we keep those words so that people can follow what's going on. But yeah, we shouldn't be really separating them.
So Innocent, do you want to pull this session to a close? And then we go into the general discussion?
Yes, okay, yeah. Thanks, Davies and Safaa, for that. And yeah, if anyone else has an additional question which comes up, please, you can always ask the question later in the coming session, or Safaa and Davies are there with you. Unfortunately, I couldn't join. And yeah, thanks everyone for you have been a wonderful audience. Yeah, enjoy Page. Over to you, Colin.